Math always works. Unless you want to divide by 0. One thing that can make math even more fun is to make it part of a physics problem. So let's make it a physics problem. All right. And now, the projectile motion problems. And I will guarantee you that on that first test, there will be a projectile motion problem. It probably is not going to be, the nice simple one that we're about to start out with. It depends upon my. So I'm going to take you through the basics of one here, and then I'll take you through probably the hardest projectile motion problem, and figure that the actual one you'll use is somewhere in between. So I have something getting launched at, let's say, 50 meters per second, at an angle of, let's make it 55 degrees, from the top of a cliff that is, we'll say, 40 meters tall. And I want to know, where does it land? We call that R for rain. So things can go.
Is air resistance involved?
I think Ben summed it up right there. Ignore air resistance. Because air resistance makes this a incredibly complex calculus problem, or a real nuisance of computer program problem.
Wait, is that a regular R or double R?
That's a regular R. That's just the letter to represent the range. We will make the assumption that this is Earth. The Earth. Not some imitation. All right, so there's a big fundamental concept that we need to get across here, and I'm going to do one more quick glance to see if I actually find the equipment that I was looking for the other day, but could not find. I'm still not seeing it. So what I'm going to do is plan B. I'm going to take 2 markers here. I'm going to flick them off the table. I'm going to use the notebook here. I'm going to flick them off the table so they both go off the table about the same time. The black marker here is going to be traveling faster than the whatever color that is, brownish. We'll call it brown. So the black marker will be traveling faster. So you would expect the black marker is going to land farther from the table than the brown marker because it's being shot horizontally. So the brown marker is just going to do this. This is brown. Black is going to do this. It's traveling faster when it's coming off the table. And so the question is, which will hit the ground first? If they both come off the table at about the same time, which will hit the ground first? So the choices are black, the one traveling faster, brown, the one traveling slower, tie, or they burst into flames on the way down. Let's just assume this is not it. So I'm just going to preempt Brandon 40 minutes for that one again. Now, have an opinion. Which one's going to hit the ground first? Have an opinion whether you can justify it or not. I'm not going to ask you to justify it. Just based on gut feeling or knowledge, whichever one you need. Who says black's going to hit the ground first? So I think that was 4 if I counted right. Who says brown's going to hit first? 2, 3, 4, 5. Who says it's going to be a tie? 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 18, so either I missed somebody or someone didn't vote. Shame on you if you didn't vote. That applies to November 2. Please make sure you vote. Primary 2. Don't forget the little ones. All right. Now let's do it. Place your side wagers now before we do it. I say that, but gambling is wrong. Don't gamble. do this with some level of coordination here. If you could move your bag in case and I'm gonna move them this way also in case the black, like, hit it so the black one clips that corner. All right, here we go. Now, I assume you saw it. Trying to think where I could do it so that, we'll do it right over here. It's off video. Go in the other direction. All right. Which one hit first? Did it? That's good. It's great. It should have been a tie. Now it wasn't, considering the black was traveling significantly faster, especially the first time I did it. How fast I was coming off the table really did not seem to have much of an impact. Now it's the question, why? I'm not going to ask you necessarily to judge, so that's what should have happened, assuming they actually went off the table at the same time. Why do they hit about the same time? Keelan?
It's being affected by the same gravity, like same rate, same forces are down upon it. That makes sense.
They're affected by the same force of gravity?
Yeah.
What do we generally call the force of gravity? G-force? If I want to know what the force due to gravity, or what the force due to gravity acting on me right now is, how would I do it? That would be very difficult to figure out what the value is when jumping. All of you have done it at some point in your lives. You just don't know it, I guess. Fall? Ooh, that's also a good one. Let's go for the visual. Now, if you've never actually done this, you probably should visit the doctor. Today, the force of gravity acting on me is, well, that's off. Because right now it's saying it's about 190 something pounds and I'm over 200. So, or maybe I just lost a significant amount of weight. There we go, weight loss by stepping on a broken scale. Sorry to see that thing finally going. This is part of my inheritance. All right, anyway. So, your weight. Your weight is, if you're near the surface of a planet, your weight is, or planet or moon or something large like that, the force due to gravity is your weight. So, if it's the same force due to gravity, if I take that literally, I don't know if that's the intent of what you were saying, the literal force due to gravity, that means you're saying that the markers weigh about the same, which is quite possible. I assume that they are close to each other. Suppose I did these two and flicked them off. Which would hit the ground first? This one weighs more.
The one that weighs more?
That would hit the ground first?
Yes. No, it's like weights to the same. It's the same.
So you're still going with the same?
Yeah, because the weight. Oh no! Don't throw something wrong though.
You said the weight. I mean, this weighs more than this does.
No, I'm talking about the weight. Like how do I explain it? What the Earth's gravity is the same amount.
No.
That makes sense.
So I think I know what you're trying to say, but the words that you're using, no. The force of gravity that the Earth exerts on each is different. That's because this weighs more. That's.
So hold on. So if you dropped it, the test we did last time, set them off the table, you dropped at the same time, they will both hit the ground at the same time?
Yes?
So just because you threw it on the table at the same, at different times, it changes? Because when
No,
it's heavy-
they're still gonna hit the ground, they should still hit the ground at the same time, but it's not because the force is the same acting on both. There's more force pulling on this than pulling on this.
Okay.
Part of this is a sneak review in the chapter 4. Let's just do the quick example over here. We'll sling the heavier one. There's nothing breakable in there, so. I suspect it wouldn't do any damage, but just in case. So they did hit about the same time.
Wait, so I was right?
Yes, but the wording that you used for Y was not right. What was the same for both? It's not the force due to gravity.
The same force?
No, not the same force. Chris?
Acceleration.
Yes, they have the same acceleration. A quick reason why the more weight, the one that has the greater force acting on it does not accelerate more, it's harder to move. Imagine, trying to think of extremes here that probably weigh more than anyone in here. We'll just assume that I do. You outweigh me? All right, so you're pushing Rodrigo and you're pushing Brianna. Who's going to be easier to move? I would assume. Let's put them on ice just to, eliminate the fact that they get into a stance. So there is more weight acting on this, but it's also harder to move, and it balances out so that they have the same acceleration. The other key thing, that horizontal piece, the horizontal is independent of the vertical. So when we solve a problem like this, we break it into a horizontal and vertical problem. So let's do it. 50 meters per second at a 55-degree angle. How much of that is horizontal? How much of that is vertical? Well, we've just gone through several problems. This would be 50 times the cosine of 55 degrees. And this is 50 times the sine of 55 degrees. Since 55 degrees is greater than 45, I would expect the sine to be bigger. This value should be bigger than this one. Is the sine or the cosine? 38.3. All right, and the other one?
28.68.
All right, we got. Oh,
Yeah, it's
40.96. All right, we got back up, we got nodding back there. All right. So we're gonna solve this like two different one-dimensional problems. That's what chapter 2 was, the one-dimensional problem. Now we're gonna do two one-dimensional problems. So I'm gonna set it up with first, let's figure out what we know and what we don't know. We have displacement, initial velocity, final velocity, acceleration, and time. So we have horizontal and we have vertical. So, what do we know?
You know, the initial,
Initial velocity?
yeah, you said it was 50 meters per second, right?
Yeah, it'll be meters per second. So, oh, who put degrees there? All right. So which is which?
Sorry, I might have missed something important. I know the final velocity is going to be 0, right?
No. Hold that thought. Let's do the initial first, and then we'll talk about why it's not 0.
Would it be negative eventually? Because I can, never mind.
You're jumping ahead. What are my initial velocities here? I got two, I got a horizontal, I got a vertical. What am I writing down?
28.68 for horizontal.
28.68 meters per second. And vertical?
40.96 meters per second.
80%.
We just did something incredibly important there. Besides putting down the information that we know. Anyone want to take a shot at what we just did that's going to affect the rest of the problem? All right, we'll get back to that. All right, so let's get to Joseph's other comment about the final velocity being 0. I want to know at where it hits from the bottom of the cliff. That is the typical language used in physics textbooks and physics problems. What we are actually going to find is how far from the bottom of the cliff is it just before it touches the ground. Even though we don't state that, it's supposed to be understood. Now, what happens, why is it that we cannot have it hit the ground in terms of actually solving?
Make it too easy.
It might bounce or it might not, we don't know.
Make it too easy.
Well, and wrong, but
It'll mess up the equation,
why?
because it'll zero out acceleration in one of them at least.
All right, or using slightly different words, acceleration is not constant. Once it touches the ground, we have another force in play. Acceleration is not constant. We can't just use the formula straight up.
Gotcha, okay.
It does make it a whole lot more complicated. All right, what else do we know?
Acceleration is a downward force of 9.8 meters per second squared.
Let's work on the language. Say it again.
It has a acceleration is negative 9.8 meters per second squared.
Okay. Yeah, you said the acceleration is a force.
Sorry,
Negative, why negative?
because it's going down and I like negative to be down.
Okay. So what was done here that was so important for the rest of the problem?
We determined
made
which way up
two
was.
Sorry, Brandon?
We determined which way up was.
I'll go with the spirit of that. We determined up was positive. Up is always going to be, that way, whether we like it or not. But as soon as we wrote down 40.96 meters per second here, because this is positive, we are now saying up is positive, which means this has to be negative.
That's true.
If
for
that
both.
had been negative, this would have been positive.
Is that true? That's true for both horizontal and vertical, correct?
Well, the horizontal doesn't care about up or down, but we established up is positive. Hold that PJ direction. Now, and as soon as we put that as positive, we are establishing to the right as positive. Is that what you meant?
Yes.
Okay. So putting the initial velocity, we've established what our coordinate system is. And now, what else do we know? We know,
Do we know the displacement possibly with the height of the cliff?
all right, so is this a vertical displacement or horizontal displacement? Say it again?
Vertical?
Yes. I do, at this point, most people have horizontal and vertical taken care of, but it's not necessarily true. For those who are still struggling with which one's which, you can always ask on a test, but the horizon runs horizontal. There's a reason those words are very similar. So what is the vertical displacement?
40 meters. Negative 40.
Somebody just whispered it. Yeah. Because we start here, we end up below, and we said up was positive. If you don't like that, blame Joseph. He's the one who said it. So this is negative 40 meters. If you put a positive there, then you're basically establishing how we'll be working with at what point it is 40 meters above its starting point. All right, and this is what we're trying to find right here. This is R. We know one other piece of information. And it's not time and it's not final velocity.
Is it the direction of the final velocity?
Oh, I think we know that this will be negative and that will be positive, but we don't know the actual angle though.
Horizontal plus or accelerations.
Or horizontal acceleration, this was, some people get intimidated by my look. If you've seen the video, you know, that was my trying to hear look just then. So what is the horizontal acceleration?
None?
I'll nitpick that one at some other time. 0. There's no horizontal acceleration. When it's in the air, the only force acting on it is the force due to gravity, which is down.
Oh, so
Nothing's acting horizontally on it once it's in the air.
that's because air resistance is a number.
Correct. If we threw air resistance into it, then
So probably-
both of these numbers are gonna change.
Okay.
And these numbers, and actually you'll end up with a formula because air resistance depends on how fast you're going. So the air resistance is not constant throughout the whole thing. That's why it gets a real pain in the butt too. All right, now, at this point, this is all the information we know from the problem. It's a matter of trying to solve for it, solve for R. We obviously can't solve for R right now because we know only 2 things. We need to know a third thing here. And there is one thing that binds them. I said they're independent, that's a little bit off. This object is in the air as much, for the same amount of time vertically as it is horizontally. And in quantum physics, even in quantum physics where almost anything goes and you can have all sorts of different possibilities, even in quantum physics, they have to be the same. The time is the same. So we have to solve for time using vertical information in this problem. And then once we have that time, we can solve for R. So, the K formulas. As a refresher, we have VF equals VI plus AT for the vector symbols. We have VF squared equals VI squared plus 2A dot delta X. That's supposed to be a delta on an upside down part. And then we have the 2 displacement ones. So we have displacement is equal to VIT plus 1/2 AT squared. And delta X is equal to VI plus VF over 2XT. All right, so we got 4 equations right there. We're trying to find time using vertical information. Which equation?
Third one, since you don't have final velocity.
All right, so using that third one there, we got negative 40 equals 40.96t minus 1/2 times 9 point, or plus 1/2 times negative 9.8 times t squared, which is negative 40 is equal to 40.96t minus 4.9t squared. Now what?
Solve for T.
Okay, how do we solve for t?
Move the 40 over so we can do the rest.
So we do what?
No, can I take right there? And, quadratic
Quadratic what?
formula.
Okay.
Did that.
Yeah, although we're sort of past the PEMDAS stage. You could bring 40 over and absolutely nothing wrong with that. This is just one of my own things. It's not wrong if you add 40 to both sides. You do need to set it equal to 0. Personally, I just like the first term positive, and that's just a me thing. I don't take off, I'm not requiring that. It's just something seems wrong about the first term being negative for childhood scars. All right, so we have 4.9t squared minus 40.96t plus, minus 40 equals 0. And so t equals 40.96 plus or minus the square root of negative 40.96, that whole thing squared, minus 4 times A times C over 2 times A.
Did you simplify?
How did you want to simplify it?
No, I'm saying.
There are things that you could do, I don't know if it makes it any simpler though. If you want the first term to be 1, you could divide every term by 4.9, but I don't know if that makes it simpler. There will be 2 answers, so let's make sure that we get both answers. If you end up with a negative under the radical, we've talked about this before, if you get a negative under the radical, that means that the problem is either impossible or there's a mistake somewhere. So in a problem like this, imagine if I throw something off a cliff, is it possible, is it impossible, or does the possibility exist that it would not actually reach the ground below? It does not seem likely that if I throw something off a cliff, it will land at some point. So therefore, I should have an answer. Actually, I have, again, 2 answers. That's negative already, so it's negative B.
Oh, no, wow.
You're back, all right.
Good.
And that's why you show your work. There, we'll have, at the end, we'll get the 2 answers, then we'll talk about why they will make sense, or how can you check, just to see in case you, because if you were off by that minus sign right there, if you had a negative right here, there's a conceptual way of determining whether it makes sense or not. Yeah, the tension's mounting. Some brave soul will be the first one to just shout it out for everyone else to hail you as a hero, or revile you as the villain you are. So you look like you're ready to go.
Okay, 9.2424,
9.2424.
negative 0.8832.
8832 units.
Unit second.
All right, anybody else get those same 2 answers? You got something different, Keelan?
Yeah, but I know mine's not right.
Okay. I am expecting 1 positive, 1 negative. Let's see, 50 meters per second. It makes sense that the negative, yeah, that makes sense-ish. Oh, wait a second. Wrong things. Yeah, but this makes some sense. Be nice if we got confirmation then. Cassandra, you got the same thing?
No, I didn't.
Oh, what'd you get?
So I got 207.34.
207.
Yeah.
Ooh, that seems awfully high. Did you forget to do the square root?
No.
Oh, okay. Did you divide by the 9.8?
Yeah.
And what's the lesson? Yes. All right. What's the radical piece?
Is it negative 18.64?
As the final answer?
No.
Or the radical piece?
The radical.
This part right here, maybe after you take the square root? Or before?
Yeah, after.
You got it. Not necessarily negative, I'm not quite sure where that one comes in.
Is it 18.64?
Is it 18, is this 18.64?
I got 49.6.
Yeah, that's it, I got.
All right, so you have 40.96.
49.
plus, I'm sorry, I got nothing here, 49.61 over 9.8. That's what we're dealing with here. When we eventually come up on consensus what the answer is, every person in here, if you don't have your calculator, please make sure you know how to do this with whatever calculator you plan to use on the test or quiz. You got the same answers as blank, different names for it. Jump down. I was getting the H. Sorry about that. All right, so we have 2 people with this answer.
I got the same answer.
We're up to 3 now. 4. On a roll. Same thing? Got the top one? Well, if you got the top one, then the bottom one can't be too far behind. Fortunately, the top one is the answer that we need for this problem. The question is, what does the negative answer mean? Why are there 2 answers? And how did I know one would be negative? I can set up a problem so they're both positive, or set up a problem where they're both negative. But this one I knew was one positive, one negative, and it was not because I've done these 1,000 times.
Time cannot be negative. The time cannot be negative.
Then what does that negative time mean?
I mean,
You refuse time to be, time actually can be negative. Because if I start the clock now and make time, this time is equal to 0, then when you entered the classroom, that was at negative time. That's what negative time means, it's before you started the clock. When did the clock start on this problem?
Nobody put a place before.
In terms of the problem itself?
Start at 0.
Sorry, Rodrigo?
Start at 0.
Okay, what
When the
point
object-
in the problem was time equal to 0?
When the object left your hand?
Yeah, or whatever launched it. So the point of launching, this is when time is equal to 0. So negative time would have to be before that.
So would that would be when you were carrying?
No, it has no idea that I was carrying. Think what the
When it
math
was
is.
in place? When it was in place?
No, it's, the problem doesn't know about me. We fooled it. That's why it has a negative time there, because the problem doesn't know that I was involved. The problem, all the problem knows is that at this point, the math, it says, oh, we got a parabola. I have a parabola here, what are the 2 times